Right. Okay, once again, good morning, everyone, and welcome to our first webinar in 2025. So we had a small pause for the winter break, and now we are back. So I'm honored to introduce our speaker today, Dr. 𝒂𝒂. She's an assistant professor at the University of Texas Health Science Center, Houston at El Paso, Texas. Thank you, Dr. Deema, again for accepting our invitation and to share your wisdom on emerging concerns with the forever chemicals and your intriguing research on developing engineering solutions to tackle this persistent chemical from both water and also from the wastewater. So to tell you about the Dr. Deema, so she is a passionate researcher and engineer with a multidisciplinary research background, and her expertise extend to selective membrane materials, electrochemical processes, water treatment and wastewater treatment, reuse, and also resources recovery. So she holds a bachelor's degree in chemistry with a minor in physics from the University of Texas, El Paso, and also a PhD in material science and engineering. So she has both the knowledge that we need for the water treatment and wastewater with the chemistry and also with the engineering perspective. And she has led and contributed to multiple federally funded projects. And she had done groundbreaking research on electro-driven separation processes, membrane development, and also the PFAS mitigation. So we will hear more about from her. So before she joining the UTHealth, she worked as a principal scientist for the Hazen and Sawyer, and also she worked as a research assistant professor in the civil engineering department for the University of Texas, El Paso. So there she dived into the inland desalination, industrial wastewater treatment. So we are truly fortunate to have Dr. Deema with us today, and all of you please join me in welcoming her to this webinar. And I know this 1 hour may not be enough to talk all about her fascinating research work, but let's try to grab the most out of it. So Dr. Deema, so over to you.
Thank you, Dr. Delanco. I appreciate it. And again, it's my privilege to be here. I am wearing red to show my support for your colors today, for your school. So, you know, go Southern Illinois. I appreciate it. I am honored to be here today. Again, I'm in El Paso, Texas, and my former position as a postdoc, I was the interim director for the Center for Inland Desalination Systems at the University of Texas at El Paso. I've since kind of moved to the UT Houston School of Public Health that has a campus here in El Paso. And so I've pivoted from being kind of a pure engineer as a postdoc and looking into, energy savings and technologies and trade-offs and that kind of thing to more of like a dynamic public health aspect. And so I'm kind of going to talk today about where those things converge. But as mentioned, my background is in material science. So I'm not a pure civil engineer. I have a lot of respect for civil and environmental engineering. And as a material scientist, my background has been in more of the membrane materials and looking at that. So today I'm going to be talking about some emerging issues in water treatment where it concerns public health. So good morning to you all, and thank you again. So to start with, what is public health? And I needed to figure this out for myself when I started here. What is the impact of what we do on the public, and why is it so important? So from a standpoint of public health, essentially, if you were sick in the 1700s, it was your fault. You were probably morally and spiritually bankrupt. You needed to heal through prayer and isolation, and you were quarantined. So that's kind of how we dealt with things in the medieval times. And then after the 1700s, there was a lot of there was a lot of New England cities that were founded in America that essentially made permanent councils to sort of prepare for public action. Somewhat in the 1800s, around 1850, the time that Charles Dickens was alive, they made this guy, Chadwick, made this report to the general public where he was saying essentially, if you were a noble person, you were dying at 36. You were dying at the age of 36, and on average, a laborer was dying at the age of 16. So everybody kind of got together and said, this is our workforce is just dying out and we need to figure out what's going on. He wrote this report discussing the sanitary conditions of the working class and why people were dying so young. And this sort of caught on as we established America with these New England colonies. And there was two major reports that sort of hit the public, which was this general report on sanitary conditions published in London, and then also another report that was out 20 years later in Massachusetts. And so these reports essentially came together and said, there's a major innovation that we can do here to maintain our labor force and to maintain the working population, which again, I'm going to kind of put in air quotes, the working population is what we care about, right? If we don't have people working, if we don't have a way to establish industry and make sure people are surviving, we don't have an economy. So it wasn't necessarily like a benevolent type of development. It was more a necessity for the working class. So the major historical innovations around public health engineering came with removal of sewage and the removal of waste. And this will kind of translate later into modern wastewater treatment. But these two reports really pushed out that we need to have sanitation for the public. If there's no sanitation, there are no living conditions and people will die easily and readily. So these things can be prevented by urban planning. And this is sort of a foundation for civil engineering today is we engineer structures and we engineer plants and we engineer environmentally, friendly things like wetlands and all these kinds of things around urban development and population growth. So finally, in 1877, Louis Pasteur proves that there is such a thing called germs. And even though you can't see it with your eyes, he injected himself with anthrax and then cured himself, thus proving that you have a bacteria responsible for an illness and this can be vaccinated against and we can prevent this. So essentially all of these innovations move towards taking bacteria out of water, bacteria from unhygienic practices, taking all of this bacteria from fecal matter out of water. And all of a sudden, people started living longer and things got much better. So these are the two major key drivers in public health progress. And, we as engineers like to think in terms of maybe energy consumption or cheaper materials or something that's going to drive the cost down. But actually, what you're doing is improving living conditions across the general public. You might not think of yourself as a medical doctor, but in fact, you are contributing to medical science. So these drivers were innovations around scientific progress and obviously evidence-based practices, which there's a lot of opinions about vaccines today. And there's different things about vaccines, but I think we can agree that polio is no longer part of the human race because vaccines somewhat work. So scientific progress and evidence-based practice are part of this public health practice. And then also the very important thing that we don't maybe take into consideration as engineers is that we are making plans and we are organizing public authorities to make decisions around this planning for the public, for what's in the public good. So as we plan out utilities, as we bring in more treatment technologies to deal with, again, population growth and volume, we're actually organizing public authorities to make decisions on behalf of the public for the better good. So where are we today? Why is any of this important? Because today, I'm talking about the 1850s here in the prior slide, but here we are today. This is a report that came out to the World Health Organization, and as of 2019, 1 in 3 people globally do not have access to clean drinking water, and 1 in 2 people globally do not have access to sanitation services safely. So this is still very much an issue today. This is not going away. And even though we made these progress points in the 1850s, it is 2019 and we're still here. So what are we doing about it and how can we address these calls to action? One of the biggest challenges we have is as engineers, there's a massive interdisciplinary community. There's environmental engineering, there is chemical engineering, there's civil engineering, there's now water resource engineering and these kinds of things. So there's actually a very broad interdisciplinary community that we all work in as engineers. And so what we want to try to do is facilitate access to the exchange of best practices and improve the knowledge and dissemination of what these best practices are and get that information to the public and make that information available for decision making. The next biggest challenge we have is regulation, and we'll talk about this later today, but we've got to strengthen communication and take action to implement regulation, and we need to make this regulation around what is sustainable. So finally, always a challenge for everybody is money, getting the money to make these changes and convincing people to put in money to make these changes and convincing people that their money is being well spent and that these decisions are important and impact them. So, pursuing advocacy, again, networking and promotion is not something you think about maybe as part of your role as an engineer, but it is. It actually is. So, as far as I'm sure a lot of people in your department have heard about One Water, the concept of One Water, and that essentially is water reuse. We have a hydrological cycle. Things go, into the atmosphere and they rain down on us. So we're really not able to just discard waste and that not come back and bite us as environmental engineers and civil engineers. So this is sort of a diagram to go through how many of these processes essentially get recycled. So you have a drinking water treatment plant, that water goes out to the community. People are then, flushing the toilets and using their sinks and everything. All of that goes into piping systems that come back to a water resource recovery center where it might be a wastewater facility. It might just be like an actual recovery center and a waste treatment plant. And then this is sort of the future where we're going, which is advanced water purification, taking that waste resource and putting it directly back into a drinking water plant and treating it again. Or you can have de facto water reuse, which is kind of where you put it back into the environment and take it out again. And we'll look at that closely. But even if you have the waste coming out of the wastewater treatment plant and you're not going to drink it and you're not concerned about that, the treated wastewater goes into the environment and you're going to see it again because, again, rain happens and we discharge, rain runs off into the river and then we pull that out and make it drinking water from a surface drinking water plant. So this One Water concept is sort of like we really can't get away from a waste product as environmental engineers. It's just going to go back into the environment and it's just going to make a treatment process later on more expensive and something to deal with. So as I mentioned, I'm from El Paso. We have a lot of, we have a large desalination plant here and we have concentrate that comes off of that that's very salty. We put it back in the aquifer. If it doesn't get diluted and it doesn't rain, we're just treating saltier and saltier and saltier water. So we'll talk a little bit more about the impacts of this with certain things that are in that concentrate here a little bit later, like PFAS. But looking at this diagram, these are some emerging issues that are coming out of each and every one of these recycling processes. So you have water resource and production, you're making drinking water, you want to optimize that. We want to make that as cheap as possible, and we want the taxpayers and our clients not to pay very much for that, or not to pay too much. There's different technologies to address advanced treatments like advanced oxidation processes and that kind of thing to try to make, things better, but sometimes they also introduce more problems. There's the impact of climate change. So as we see more rain and greater storms, stormwater can run into drinking water. And then you have boil water notices like in Houston or in different cities in Texas, Austin, where they have a stormwater event and that runs off wastewater into their drinking water. As far as the distribution system, we chlorinate water when it goes into the pipe so it doesn't grow bacteria, and that disinfection byproduct can create other byproducts in the pipe. There's a lot of analysis on leakages in pipes. Some of these pipes in our infrastructure are 50 years old. And then there's things like corrosion. Like I'm sure everybody here is probably familiar with Flint, Michigan, and the lead in the pipes and that kind of problem that people have. So again, this whole diagram is kind of a complicated diagram, but you can see all the arrows go back into one source. So there's reclaimed water, reuse, reused water, and then there's source water. And sometimes this all gets blended into one thing. So with regard to the public, the types of things that engineers do that are really important are, one, we don't just solve problems, but we educate people on these issues. What are you facing? So we might not think of that as part of our job because we're solving the problems, but in solving the problems, you are also communicating to the public the importance of the problem and potentially how regulations will impact them. There's quite a few focuses on public health engineering with improving facilities. I think if you're in a consulting firm, there is a lot of talk about retrofitting wastewater treatment plants, and that can be a challenge in itself because you're, again, using aging infrastructure. We identify risks. So we look out for things that are coming up on the horizon, like climate change or population growth or both. And we look at our infrastructure and say, can we handle this? There's another emerging issue with AI. If you're Meta or Google and you're trying to implement AI, there's, a concern about how much water is available to those GPUs as opposed to the public. So if you're going to put in an AI facility somewhere, you call the utility and you say, hey, do you have about 20 million gallons per day that you can spare for our facility? And if not, they go somewhere else. So there's identifying risks, developing solutions, and being sustainable. So the kind of skill sets that you need to do these jobs are, you need to have good communication. You need a good knowledge base, which I'm sure everybody here has a great background in their environmental or civil engineering disciplines. And you need to be good at problem solving to do that. But I think communication is something we as engineers sometimes don't think about as being that impactful, when in fact, that's how the public finds out about stuff. So how does this really influence us, and how do we see this playing out today? So I'm going to bring this to a modern topic today and try to bring in all of these factors about communication, regulation, and best practices. So people probably have heard of PFAS, right? So at the national level, we are now potentially regulating drinking water for PFAS. So this all came about because the public heard about it. This is a really popular film called Dark Waters that talks about the sources of PFAS and how we got here today, where PFAS is in every single person's blood. Even unborn babies have PFAS in their blood. So there's now been growing pressure from the public on the Environmental Protection Agency to do something, especially from a perspective where these are commercial companies that are profiting off of these chemicals, and just then now the environment has to deal with them. And we have to deal with them as individuals, eating it, consuming it, drinking it. So these are some of the nonprofit organizations, non-government organizations that put pressure on the EPA and use the public support to kind of help implement these rules. The Environmental Working Group is one of those groups, and the Southern Environmental Law Center is one of those groups. So again, engaging the public, engaging regulators through legal action, because someone's making money off of this. Even more important, aside from putting pressure on the EPA, people have put pressure at the state level to put on regulations, and that puts pressure on federal agencies to follow suit. So California, for instance, may have overregulated some of this stuff, but that has put pressure on the federal agencies at the national level to do something about it, because states are taking things into their own hands. So again, this is a crossroads of education and regulation in this emerging field. So this is how fast this is sort of happening and how recent it is. In 2022, CERCLA, which is essentially the Comprehensive Environmental Response, Compensation, and Liability Act, it's also called Superfund. So seems like a big acronym, but you could think of it as Superfund. They propose the designation of PFAS as a hazardous substance. So you will be reported if you're making something that's 1 pound per 24 hours. If you make a pound of PFAS material every 24 hours, you need to be reporting this to the federal agencies. So drinking water plants are not yet exempt from being named as responsible parties. This is where it really impacts us as taxpayers, consumers, and as engineers. We want to solve this problem. As taxpayers, we don't really want to pay for this problem because we didn't make it. And as consumers, we don't really want this in our body. So the problem is we have a law, but we're not sure where to aim that thing yet. So drinking water plants probably shouldn't be on that list, but they are. So if you're basically, as of January 31st this year, the EPA listed 9 PFAS chemicals, which are polyfluorooctanoic acid, PFOA, the sulfonic acid form, PFOS, and then these other ones that are, I'm just going to not name them. I'm not, so that they're not. Feel free to ask me in the questions if you want to know what these compounds are. But yeah, so essentially these are mutagenic and carcinogenic, and we have determined that at least these 9 compounds are, there's over 500 PFAS compounds, but these 9 compounds are going to be regulated. We do this in water and air treatment as well. For instance, the EPA regulates air pollution based around 16 priority polyaromatic hydrocarbons. So they just kind of picked like 16 of the most prevalent and destructive chemicals and said, we're going to track that and regulate that. So this is very similar in that these 9 PFAS do not constitute the number of chemicals that are actually out there today. There's a lot of them, but we're going to start with these because these are the most destructive and damaging to human life, but also they're the most prevalent. So this listing has given this groundwork and framework for the EPA to start looking at drinking water plants and say, we don't want these in here. This better not be in drinking water. So this is sort of a kind of an overview of what PFOA looks like. And it's again, these polar groups are what a lot of people are attacking with technologies, but also these polar groups are what make this bioavailable potentially, and why we are looking at regulating those as opposed to other types of PFAS. Same thing with the sulfonic form of it. This sulfonic acid and this carboxylic acid group make these somewhat reactive, and that's one of the reasons why they're considered some of the worst. So these are some of the minimum risk levels that have been identified by the CDC, the Centers for Disease Control, and why we're making minimum contaminant levels in drinking water around these PPT levels. So PPT, parts per trillion. So at PFOA, when we look at PFOA, 78 parts per trillion in an adult is considered something that is of concern for the CDC. And where are these sources coming from? Where are we getting this PFAS? So it's very hard to determine that. It's in our clothes, it's in all of our products, it's in Teflon tape, in Teflon. But when we identify it in drinking water, it's a big problem because, right, we're consuming water every day, all day. So people have focused on starting there for regulations. And where do these things end up? What should we be looking at, again, as engineers? When we take samples, where is this PFAS going to end up and where is it most likely to concentrate? So usually it's in the residuals of your treatment. So we have here a dissolved aeration sort of floating thing. Wastewater comes in here and we aerate it, and we're using some bugs to kind of remove organics and that kind of thing. But then all of that kind of drops out and becomes sludge. And we can also throw in some coagulant material that's going to flocculate. And then we put it through maybe a dewatering belt and a gravity thickener. So we separate all the solids out. And this is usually where PFAS ends up in a wastewater treatment plant. It usually ends up in the residuals. So that's nice because we can take it out as a solid and deal with it. However, there's still some that's left in the water, and we're able to put it through a membrane process if you have one. Some people don't use a membrane process, and so it's just in their drinking water. But membrane processes are a well-recognized technology for 99 to 99.9% removal of PFAS. So membrane technologies like reverse osmosis and nanofiltration are 30 years old. They're very well accepted by the EPA as a treatment technology that's highly capable. Again, as civil engineers, environmental engineers, we know there's a lot of exciting new developments out there, but people cannot implement them right away because there's not 20 to 30 years worth of data. So if I give you a palladium catalyst, then I'm like, this is going to work. It needs to be time tested, it needs to be taken out there. How much does it cost? How long will it last? So these technologies are at least 30 years old, and they've definitely been time tested and are well accepted across a lot of range of conditions and that kind of thing. So it's great that you can take PFAS out from drinking water with the membrane process, but where does that other stuff go? Where does the stuff go after we've taken it out? We concentrate it. So we have to deal with that as environmental engineers. This is kind of moving all over the place, but now that we know where these things come from and where they go, what can we do about it? And as engineers, again, we're kind of driven and also held back by regulations. So we can't just make suggestions unless at the state level you pass regulation, but we can't just make suggestions to take it all out because it's not necessarily regulated. So just to kind of give you a timeline on how tricky it is as an engineer, especially if you're an environmental engineer right now. Basically in May 26th of this last year, 2024, you had an issue where Tucson International Airport said, we're going to designate this a Superfund area and we want this cleaned up. And we know that this is getting in our drinking water and we didn't put it here. So as of June 11th, in 2024, the Air Force requested that the EPA pauses this order, and we're not going to do anything about it because we're not really sure we're legally liable. That's what the Air Force said. And so in June 28th of last year, the Chevron ruling came out. And I don't know how many people here are familiar with the Chevron ruling, but the Chevron ruling essentially gave the power to federal agencies like the EPA to make regulation based on people's professional input in science. Right now, because the Chevron ruling has been reversed, we now have to pass a law in order to make that regulation. We can't suggest it as the EPA anymore. We have to actually get it through Congress and pass an actual law. So that's changed a lot. I'll get more into how this impacts real people in a minute, but basically after June 28th, essentially the Air Force was like, we're not cleaning this up. So the EPA issued a letter to the Air Force saying that they need to clean it up. Here's the 30-day extension. Give us a water treatment plan. And then they came back 7 days later and said, you can't make us do that because the Chevron ruling says you have no power to do that. So we're not going to comply with that. And, thanks, but no thanks. And so just to tell you how fast this happened, in April of 2024, the EPA passes regulation around PFAS. And by June, the Supreme Court was like, have fun enforcing that. So that is, in a nutshell, part of why public advocacy and engineering kind of intertwine with each other. And it's kind of a kind of a big problem, but it's more complicated than just saying we want to fix the problem. So again, going back to the actual engineering side, these are different approaches to treating PFAS and taking care of it. Again, we can put all of our water, whether it's concentrate or drinking water, through an adsorption process. And this is great because it's easy, it's cost effective. But one of the cons of this, one of the downsides, is that the treatment effectiveness isn't great. You might have to rechange your granular activated carbon frequently, depending on where you are. The other technology you can use to remove PFAS from drinking water is high pressure membrane. So that's great because it works. You can remove all the PFAS, so it's not selective to some type of PFAS, and not, it's just an exclusion. It's just a barrier. The downside is it costs a little bit more. You have an energy consumption cost. You have to use pressure to push that water across the membrane. And then the biggest downside is the concentrate, is that once you've pushed the clean water across the membrane, there's all this stuff that's rejected that's left behind. So now we have to put that somewhere. And if you already have like a well that has PFAS in it, you can't just put that anywhere. You can't let it leach into the groundwater and spread PFAS everywhere. Knowingly, you can get sued for that. So when you have concentrate, it's like 10 times worse. It's even worse than the source water, right? So these are options we have. We can do deep well injection. We can, if we want to take our brine that has PFAS in it, inject it into the aquifers, we can do that. That's not great. Direct discharge is just putting it somewhere on the surface, some environmental, like just put it in the river. Great, great idea. You can do evaporation. Again, it's still, even though it might be a solid and you have a zero liquid discharge, you still have it in residuals and it can leach out. It can still just rain down into the groundwater and get in there. You can also do incineration or reactivation of activated carbon. So you can take this activated carbon and you can burn it and get rid of the PFAS. But still, we're really not solving this problem. We're not destroying the PFAS. We're just moving it around. We're just taking it out and putting it somewhere else. So we need to look into PFAS destruction. And these are really, really emerging technologies. We really don't have a tried and true PFAS destruction technology that has been out there for years and years and years. We have a membrane technology that will take it out for you, but again, you're still concentrating it and have to do something to get rid of it. So these on the left-hand side are types of destruction technologies. You can get supercritical water oxidation. Photochemical degradation is a method some people use. There's non-thermal plasma and hydrothermal liquefaction. One of the most common is electrochemical oxidation, and that's something I'll talk about that I worked with over the summer. And these are the contaminated matrices over here on the right side. You have landfill leachates that are really high in PFAS, all those solid residuals. You have stockpiles from firefighting materials that are really, really, really bad, that we have to essentially designate as hazardous waste. You have spent absorbents, so all that GAC or any ion exchange that you might have used to get rid of PFAS, that you have to do something with that GAC and that solid. Again, firefighting residuals. So membrane concentrate. So we can look across the state of Texas and see, different membrane treatment plants, or across the entire country and see different membrane treatment plants, and you can just get an idea of how much concentrate is made from those daily. So here in El Paso, we have the largest inland desal plant in the world, and we produce 27 million gallons per day from that desal plant alone. And that's only 5% of kind of what our city consumes a day. We consume a lot more water than that. So membrane concentrate is also like a big area of residuals for PFAS. So what are we doing about that, and how emergent is some of the technology? So this summer, I got the opportunity to work for Hazen and Sawyer, where one of our clients was a startup company called 𝑬𝒗𝒂. And we submitted a proposal to the USBR to do a destruction technology pilot with 𝑬𝒗𝒂, and they used an electrochemical destruction technology. And this was a very interesting little pilot. Again, it was one of the largest and longest pilots out there. We did a 60-day trial of PFAS destruction at the Brackish Groundwater National Desalination Research Facility in Alamogordo. This is a really neat little national lab that the USBR owns, and it has like 4 different wells within the site, the national lab. And one of the wells, well 2, is really high in calcium sulfate, but it's also very high in PFAS. And so if you do a technology on well 2, they're very serious about making sure that there is absolutely no groundwater leaks at all. There's a berm here, and all of these pipes and all of the plumbing had to be like really solid. And we were on well 1 for a long time before, doing leak checks to ensure that once we switched over to the PFAS well, we were not going to spread PFAS anywhere. So if we had a large leak, we would actually get this facility sued. So there was a lot of plumbing that was done for this technology. So here's sort of like me in this trailer. It was super hot out there in Alamogordo. It's like 100 and something degrees. And I know, Hamali, you probably miss this out here in the Southwest. The sun is just, it's Tatooine out here. I'll just say that. If you're familiar with Star Wars, it's the desert. So these were some pretty hot little trailers. And essentially we picked this membrane filtration. We had a nanofiltration membrane skid. We ran this guy at about 60% recovery, which means for every 10 gallons that we're pushing through the system, we're recovering 6 gallons of drinking water, and we're concentrating 4 gallons of concentrate. So we usually treatment plants will try to run between 50, 60, or 40% recovery, because you don't want to scale the membranes. So this was a continuous test over 60 days. And that, I'm sure if any of you guys have run pilots, you might know how challenging that is because stuff breaks and goes down. But essentially what we did was a supercritical oxidation, electrochemical oxidation with some electrodes. And so again, I want to emphasize that there are no like really commercially available treatment technologies outside of maybe Ovivo technologies, and they even purchased it from a startup. So there's a fledgling of startup companies and different things that you see when you look into PFAS that are just not yet fully established. So there's a lot of challenges with this that people are still ironing out for treatment and to kind of meet these regulations that are coming out. And I'll tell you from personal experience that the startup company we worked with as a client, they were on cloud nine in April. They were like, this stuff is getting regulated. Everyone's going to need our treatment technology. You know, the regulations are coming out. We're ready to meet the challenges and break down these technical barriers so we can meet those challenges. And by June, by the Chevron ruling, it was like a roller coaster for them. All of a sudden, oh, there's no way to enforce these rules. There's no way to enforce these regulations. So that is something that we don't necessarily consider as engineers, that the market sometimes is beholden to these rules, and they are sometimes political and sometimes they change, or it's a process to pass a law. So why do we care about any of this stuff? I'm going to kind of speed through this PFAS stuff because, again, there's a ton of technologies out there. There's a ton of research being done. But the point of all that is there's still no like commercially available treatment technology that is proven, that is time tested and has been used for years. There's a lot of technologies to remove PFAS, but there's like two commercial technologies that are like 5 years old that are for destruction of PFAS. So why do we care? It's because we are driving towards reuse. We have to use every drop that we are treating. We really can't afford to throw water away. So we're looking at ways to recover that 4 gallons in that 60% recovery equation, that 4 gallons that concentrate. We really want to get as much as possible out of that. So this is sort of a graph to show you, and you guys are where? Where's Illinois? So I'm down here, I'm in El Paso, Texas. You guys are over here, you know, and you can kind of see the whole green area. You're getting all this nice water that's coming back through your groundwater because it's raining, and you have, you know, snow and precipitation and that melt and all that kind of stuff, and rivers and whatnot. And here I am over here in this little brown area that's sort of light green. And so there's different drivers around the country for water reuse, but one thing is certain, we know that we are running out of groundwater in the country, period. We'll all face that. Some of us are facing it out here on the west and the southwest a little bit faster than, say, in the Northeast and the Mid-Atlantic, but the problem persists for everyone. And so if we're trying to squeeze as much water out of that 4-gallon concentrate as we can, we have to deal with PFAS. We have to deal with emerging contaminants. We have to deal with the stuff that's in there. So essentially, I mentioned earlier, El Paso's in a permanent drought. We only get 4 to 6 inches of rain a year. So how are we going to get people here? How are we going to sustain population growth? Well, we can import water, and that's going to be $13 a gallon. We can do direct reuse at $4 a gallon with advanced water purification. We have the desalination plant here, and we also can do surface water and groundwater. So from this chart, you can kind of see a lot of what we have done in the past is essentially subsidized by the Department of the Interior as groundwater treatment and surface water treatment. We haven't been looking at other alternative types that are more expensive. And so the time will come for everybody when that happens. And how are we going to do that? So this is sort of a conventional drinking water treatment plant. This is the cheapest way to get your drinking water out of a surface water source. You have a river here, you screen it, there's the sedimentation, the sludge that we mentioned. That sludge might have PFAS in it, but whatever, it's solid, we'll haul it off. And then you kind of get all the way over here where you do some type of filtration, and then you add disinfection, and you send that out in the pipes in the distribution system. So this is an activated sludge municipal water treatment plant, sort of the same thing, but you're collecting raw sewage instead of taking treated surface water and the river water and then treating it to drinking water, you're going to take raw sewage, collect that, get it through all of these, the primary sedimentation, biological treatment, secondary treatment, and then finally tertiary treatment. And I'll kind of hurry along here because I know we're getting short on time. Basically, after this tertiary treatment, we put it back into the river. So then we get back to this drinking water plant. So you have this kind of like relationship between a surface water plant and a wastewater treatment plant, where you have a wastewater treatment plant that is kind of downstream from a drinking water plant. So we take raw sewage from wastewater, treat it all to the point where it's somewhat drinkable, or get it through tertiary treatment, and then we put it back in the river. And then we pull that out and use that as drinking water and treat it to drinking water standards. So that's called de facto reuse. And you can start to see really quickly that if we're introducing things into wastewater treatment, we're going to deal with them in drinking water treatment, period. You cannot separate the two, even if they're at different locations and different plants. So how are we going to reuse water? There's lots of ways that we can augment water reuse in Orange County. Essentially, what they do is they get the water to a drinking water standard, and then they inject it into the ground or their aquifer, and that's called direct potable recharge. And what they found out through these emerging scenarios was that at some point in time, 10% of all their groundwater became treated wastewater, and they were very happy about that because they felt that they were managing their water issues, but in fact, they injected their groundwater with PFAS unknowingly. So another way is you can use a reservoir to do this. El Paso Water is doing this now, where they have a very large arroyo and they're treating wastewater and then they're flowing it through this arroyo where it's sinking back into the groundwater. So that's another way. But both of these techniques essentially put it back into the environment, either as groundwater or surface water. So again, these are some complicated issues surrounding that water reuse, and that we cannot really remove pollution until we destroy it. We're just pushing it around and dealing with it later. So again, these regulations for direct this is a graph on regulation for just water reuse in general. And what you can see from this graph is that there are some states that don't necessarily have any type of regulation around water reuse, around treating water to potable water and then putting it back into the environment. So all these grayed out states are states that don't have regulation. And then further, there's very few states and very few cities that are doing what's called direct potable reuse, which is treating water to drinking water standards from wastewater and being able to drink it. That's where we're eventually going to be able to be sustainable throughout drought and be drought proof, is to take the water that we're using as a population and get it back to drinking water standards and drinking it. So again, this complicates. If you're sitting in a professional firm, like I was at Hazen, there's Garver, Carollo, Trussell. There's quite a few consulting firms that you can go work for as a civil engineer, as a PE or environmental engineer. This kind of complicates your job when you look at this from a national level. There's not a one type treat all technology, and further, your clients won't demand it because these regulations might not exist. So coming up with a treatment technology is very much, a source type fit. You've got to fit it to what the customer can pay, what regulations are there, and we can't really do this at a national scale because of the lack of regulation around this at a national scale. So types of treatment technologies, a lot of people will use membrane-based technologies. That's sort of the area that I have been in, and that's a really good thing for removing microbial chemical constituents. You have a multi-barrier approach where you can do MF or micro or ultrafiltration to reverse osmosis. And then you kind of get through these other processes, the UV advanced oxidation process, granular activated carbon, and finally disinfection and sending it to the distribution system. Alternatively, if you don't have a membrane-based process, there's also very good carbon-based processes that work, and they kind of lower the energy consumption because we don't have like a RO there. So if I go to Austin or Houston, most of the time they have this type of approach, but here in El Paso, we have an RO-based approach. So again, the main takeaway here is that these are tried and true. They are very inexpensive because we're taking some surface water sources, but as you get into groundwater, you have issues with the level of salts that are there. Here we have a lot of brine, but we need to diversify the number of water sources we take in, and they're not all the same across the country. So treatment technologies, we as engineers face a lot of challenges when it comes to fitting technologies for your client or for your city or whatever, in that you don't have a technology that's a one size fits all. You've really, everything is a pilot, unfortunately. So that's why you guys do get paid lots of money, is you're de-risking that type of technology. You're looking into it as engineers. You're designing, making designs around contingencies and making designs around, what is present in that water right there. You could move 250 miles south and it's completely different. So again, the types of technologies we choose are based around mandated standards. So again, what is the TDS level requirement? What do we have to remove in order to meet standards and health standards here in this city or this state? Are the things we're removing and treating going to be compatible with an aquifer or not? Are we going to be able to put it back in an aquifer? And then are we going to have constituents in our groundwater that will not be compatible with disinfection? So if you have a groundwater source that you're treating with this RO and it has bromide in it, you can produce, byproducts by chlorinating your water, and that is dependent on your source water. And then finally, if you're going to implement uh, very advanced technology like RO, you're going to produce stuff like concentrates. So do you have a management option for that? So here in El Paso, just north of us, we have a direct potable reuse in a real small town that's called Cloudcroft. We tour it kind of every year. They have a membrane process that's been sitting there for 10 years that they have never implemented because they got to the design, they built everything, they paid for it, and then they were like, oh yeah, what do we do with the concentrate? And they said, well, just put it back in the water. And then they realized if they did that, it was not going to be unsustainable. They would just increase the level of salt that they were treating throughout the process, and they would not be able to meet their standards. So there's always a trade-off with advanced technologies in that you produce another problem. So we as engineers, a lot of times we solve a problem and make two more, and we have to consider that later. So again, this is sort of a graph that we have from Hazen on the drivers for the Orange County water system, groundwater system I was talking about. They were very proud and one of the first groups to kind of like lead direct potable recharge, which then is a precursor for direct potable reuse, which is the drinking part. Direct potable recharge, we treat it to drinking water standards and then re-inject it. So they were depleting their groundwater. They were like, let's do something to put it back. They didn't want to do something too intensive or too energy intensive. So they basically treated their water again to drinking water standards and then injected it back into the ground. So they also employed an RO and essentially had to do something with that concentrate. And they did not treat that concentrate for PFAS for like 10 years. I mean, nobody really knew about PFAS 10 years ago, or it certainly wasn't on the radar. Now it's going to be regulated. So now they're at a point where just as of last year, they were like, we thought we were responsibly recharging our aquifer, but in fact, we were injecting PFAS into our aquifer. So again, the drivers were the depletion of groundwater. Let's put some water, let's treat it up and put it back. And then we ended up like polluting ourselves. This is sort of an overview of how long it takes to make these decisions and how long it takes to do a project commercially. So you can see how long an implementation really takes at the city or state level. This is what a program really looks like. You have an environmental impact review that can take up to 3 years. You have this conceptual planning process where maybe sometimes you have pilots, but you're looking at, again, contingency plans, because as I mentioned, like there's not one size fits all. So as designers, you'll tend to like over design and make sure that, you're not going to have a problem, because once you run into the problem, it's too late. Finally, there's a selection process that takes about a year. And then there's planning all the construction, and the design can go on for a while, but this is sort of like how long it takes to say that you have a successful implementation of a utility. And so I know we're kind of out of time here. This is a lot of content, but mainly my takeaway from all this is as engineers, you are actually doing what's in the best interest for the public, and you have to make a lot of complicated decisions for people and for engineering. And you might not think about it now because you're more concerned about, fixing the problem and solving the problem and getting numbers and getting data. But in fact, what we do is a lot of advocacy for the public in making these decisions. And a lot of the public doesn't understand how complicated, how long this takes. So those are some of the challenges that you kind of face is, again, communication, regulation, aside from just like the problem solving that you have. So I will go ahead and wrap this up here and take some questions. I know we're a little bit over time, so I will give you guys the next 10 minutes to ask any questions that you have of this. And thank you so much for your attention and your time.
Thank you so much, Eva. So it was a really interesting presentation, and within this short time, shared a very broad spectrum. You covered a lot, and starting from the history, the policies, how we can treat. And for me, actually, this PFAS is a kind of like a black box. We know it's a growing issue, but we don't know more about it. But I think you clearly explained everything, and I'm sure this might have helped all our budding environmental engineers and their role. And I'm really grateful for this presentation, and thank you so much for your valuable time. So
My
if you
pleasure.
have,
Thank you. Thank you for
mm,
inviting me. So it's great. And then if we run out of time here, like I have plenty of time after this, so I can stay on. But if we run out of time, please feel free to email me, contact me for like anything you need. So any questions?
let me check the chat. So I think there is a question from Nitin. So Nitin, do you want to ask Dima herself?
Yeah, so it looks like here, given that our O system significantly reduce essential minerals.
Hi, Dr. Rima.
Yeah.
I think it will be easier. Nitin, you can speak, right?
I think she has already gone through the question. So my question
Mhm.
is in general, I'm not from the environmental, so I may not be having detailed orientation. But since you mentioned about the RO technology, and recently I had a encounter, like one of my friend, he went to the doctor, and doctor suggested stop taking the RO water because you're getting a mineral deficiencies. So, like, is it really like, especially the people who use residential RO system and they install RO system at their home and they use it, so they're getting these kind of health concern, especially people observe some dental health concerns also due to like low minerals coming from the RO purified water. So,
Yeah,
like, is it
that's a
really
great question.
recommended or like you have some other alternatives for that?
Yeah, so there's like the at-home use kind of filtration stuff, which would include Brita, at-home use, RO filtration. Some people don't trust their water. Again, this when I'm talking about RO systems and PFAS, I'm like looking at the public, again, 27 million gallons per day type of design. But to your point, what we do here with the utility to make our tap water safe is we blend. So we take that RO water and then we blend it with the surface treated water to bring up the TDS. So to your point, yes, if you are dehydrated and you're just drinking water and not electrolytes, that's the whole foundation of Gatorade, is that you have athletes that are sweating and you're sweating out calcium and potassium. And so you can get a mineral imbalance. So if you're a consumer and you don't necessarily trust your water, I would advise, yeah, throw in some Gatorade. There's a lot of powder mixes that you can get. And so if you're drinking a ton of water to the point where you might be replacing a microbiome in your system, and you're also depleting minerals, it's an easy fix by just, getting some salt or, adding some Gatorade or something like that to your mix. But there are people that use at-home RO systems, and they're about $200. You can buy them on Amazon and get them. I live actually in New Mexico, where I don't have water from El Paso water. I have it from a little system called Crua, and there's arsenic. So I do use an at-home RO system. But if you're drinking a ton of water, you essentially an RO system takes a TDS level that's anywhere from 1,000 to 2,000 TDS, ppm TDS. It'll take it down to 80. So it sounds like your friends might be drinking like deionized water, which is totally, there's distilled water, deionized water, and then RO. But for the most part, RO doesn't take out all salts. It does pass sodium. It's just at a much lower concentration. So again, if you have 1,000 parts per million or 1,000 milligrams per liter of salt, you pass it through at-home RO TDS, and you can see that it's about 80. It'll turn into about 80 milligrams per liter from that 100. So it'll take out 90 to 95% of the salt. So that's a good question, though. Great question.
Yeah,
And yeah,
thanks,
there
Dr.
are
Dima.
there's TDS tests that you can get. It's like a little pH probe. It's about $10 on Amazon. You can get a little handheld TDS meter if you're interested. And the EPA regulated TDS content is 500 ppm. So if it's anything above that, you probably should look into a filtration system. And there's Brita is a good kind of absorbent material, and it you can get the picture and it tells you when to change the filter. So, but you can imagine like that's at home, but dealing with that on a huge scale, right? Like like millions of gallons per day. So kind of easy fix for a consumer to make a consumer-based choice. But that's a great question because it is a health concern.
Yeah, yeah, Dr. Liu, you can unmute. I think I given you the access.
Okay.
Hello, Dr. Dima. Thank you so much for the comprehensive presentation. I enjoyed it a lot. So I have some questions regarding your pilot scale study. So I may miss your information for the PFAS destructive treatment after the membrane treatment. So you are using a combination of those technologies, destructive technologies, or you are comparing the effectiveness of those individual treatment units. And also, if you can introduce the background a little bit more, that will be helpful, like who is the funding agency, where is this contaminated site, and what is the volume of this membrane treatment unit. Thank you.
You got it. Thank you for that. That's a great question. So these are essentially the types of destruction technologies and the types of concentrates, but I focused on the electrochemical oxidation. And let me just put it in the presentation mode real quick and get to slide. Actually, never mind. I'll just make it easy faster. So I focused on these things in red, which was membrane concentrates, sort of the most common matrix that we would see from a drinking water standpoint. Landfill leachates, all these firefighter stockpiles, we don't really see that too much. Landfill leachates are a little bit lower priority because those are solids. So we were like, let's target membrane concentrates because everybody's using membranes to produce drinking water. This is a very concerning problem. And as we know, we're concentrating other solutions outside of PFAS. So again, we picked electrochemical oxidation, and that was because this startup company was very much in commercial progress. They were not a lab scale based experiment. They were rolling out high voltage trailers, and they're like already in landfill leachate. So they're already somewhat commercialized, and they have a supply chain to get to a customer and a client. So if we recommend them to a utility, it won't be like, wait 5 years for them to get started. They're ready to go. So we were like, all right, we wrote a proposal to the US Bureau of Reclamation, which is essentially under the Department of the Interior. So the USBR has a very nice pitch to pilot program, and it's about $250,000 of an award. And you essentially make a pitch that, hey, we got a technology, we're ready to pilot it. So I'm not sure if people are familiar with technology readiness levels. I myself am an entrepreneur and can tell you that de-risking things is a big deal because you're de-risking money. So if you are ready to get to the field in the form that you're going to sell it, that's called technology readiness level 7. Technology readiness level 1 is the idea. Technology readiness level 3 is a bench scale unit. 5 is a prototype, and 7 is like the prototype ready to go out into the field and do it on the site. So this pilot was performed at the Department of the Interior's, it's actually the US Bureau of Reclamation's kind of TRL-7 research lab. It's a national facility called the Brackish Groundwater National Desalination Research Facility, or Bergendorf for short. And I don't know, Hamali, if you ever went out there, but they always have a conference out there called the Water Innovation Networking Conference. And it's like this crazy little town, Alamogordo, but there's just all of the power players from the water industry that are out there. And I should say that this national lab is sort of like a NASCAR racetrack. It is where 𝑬𝒗𝒂's out there, 𝒂 out there. There's about 4 or 5 startup companies that are out there piloting. So it's a really exciting place to be. And this setup that you're seeing is a nanofiltration membrane skid that then sent concentrate into a holding tank that they would take into this trailer. And this is the feed tank kind of back here. Let me just sort of scroll over to show you this trailer. So they essentially had a reactor right here, and they had a 30-gallon feed tank, and they ran continuously at 1 gallon per minute. So we had to run this membrane skid at roughly 5 gallons per minute or more to be able to produce a gallon per minute concentrate for them. So that is an idea of the pilot scale. At pilot scales, you're usually doing, again, gallons per minute. So if you have a problem, it's going to be a big problem. It's not a liter per hour or a couple liters or milliliters going through a column. Like, this is all continuous based. And at 5 gallons per minute, you know, you're talking about, 60 gallons in 30 minutes or more. And my math is off on that.
What is the water quality originally before this membrane treatment unit, and what is water quality after your electrochemical oxidation? So do you create some other PFAS or other problems or byproducts?
Yeah, so that's actually a good question. A lot of the challenges in PFAS destruction are centered around how much other constituents are there. And basically PFAS was on a ppb level, and we have, calcium, magnesium, sodium, potassium at very high levels, at milligrams per liter, at orders of magnitude, 5 orders of magnitude higher than the actual PFAS. So the actual water quality here, we had about 500 ppm alkalinity. We had 1,000 plus ppm chloride, and we had over 5,000 ppm of calcium sulfate or sulfate in the water. So this is a very high scaling water that has a lot of calcium sulfate in it. We're close by with something called white sands, which is nothing but gypsum and calcium sulfate. So calcium sulfate precipitates. One of the challenges with electrochemical oxidation and PFAS destruction is that you produce a lot of OH groups, a lot of hydroxides, and these hydroxides will precipitate with magnesium and calcium quickly. So the water quality, that kind of gives you like an idea of 5,000 ppm. That's like 5 grams per milliliter of sulfate alone.
So what is the concentration of PFAS before the treatment?
Yeah, I really shouldn't just tell you too much about this, because this is under NDA with this, this is a commercial company. I will tell you that it was very difficult for them, but the concentration of PFAS in the well was anywhere between 20 to 100 parts per billion ppb. Right. And the cutoff limit needs to be PPT. So what we need here is like 90% destruction. I can tell you they did not do that. It was high. It was not as, it was a promising technology. We sent them some like brine water to test it at lab scale, but it did not work out well. I won't say it didn't work out well, because it worked, but we ran into a lot of problems with the brine. And this is a problem for everyone to look at when we look at PFAS destruction, is that you can't really selectively remove the PFAS, and it's so small. So we basically pivoted this company and another company into looking at the actual influent instead of the concentrate, because we were like, all of these problems you're seeing, hopefully we can dial it down a little bit with the amount of calcium sulfate you're seeing by just not doing concentrate. But by and large, if you have like a big treatment technology, or you have a big RO facility or a big membrane facility like in El Paso or Orange County, where they're using RO and millions of gallons per day, you can imagine how difficult it is to retrofit that and apply something that's emerging like this to destruction and treatment. So it's so emerging. Like, again, we did this is still going on. And they have changed quite a few parameters since then, from the voltage to the flow time and the residence time. So this is a reactor, and again, I just mainly want to emphasize that there just are no accepted treatment technologies yet, and we barely regulated it, and that regulation got undone within 2 months. So it's kind of a moving target for everybody. And then these challenges will exist for any of these technologies, where if you're going to concentrate, or if you're going to take a brine and try to destroy PFAS, you have everything else in there, and it's going to depend on the source water. To your point, what is the water quality coming in, and what is the water quality getting concentrated to, and what are we feeding to them? So they ended up producing quite a bit of magnesium hydroxide, and it inhibited all of the destruction. So they would go through we would go through testing where we would ramp up voltage and then pull it back. So we would try to precipitate stuff, and then when we did, we'd pull it back and try to, there's efficiency and longevity, and those things are sometimes a trade-off.
Thank you so much.
Thank you for your question. Yeah, thank you for your question. And I'll just drop into the chat here the Bergendorf link so you can see, because that's a really unique place. And I know Hamali, you've been there.
I have. It's a resource, actually.
It's a really neat place. Again, a lot of really cool startup companies are out there. I did a membrane technology way back when, and I would have loved to pilot there, because they just have the coolest stuff there, and it is a national lab. So a lot of new technologies go out there to kind of test their grit, and they do have very high fouling water with that calcium hydroxide, or that calcium carbonate, sorry. Calcium sulfate is what they have, gypsum. So, but yeah, I guess as engineers, when rubber meets the road, it's you don't know what you don't know. Sorry, Hamali, go ahead.
No, that's fine. So I think that's all questions we have. So if you don't have any other questions, then there's one more question. So Eva, can you spare few minutes?
Yes, absolutely. I'm free.
Bushra, go ahead.
Hi, Dr. Deemer. Thank you for the nice presentation. My question is about the huge gap that seems to exist between the scientists' findings and recommendations and the actual implementation on a governmental size or governmental spectrum. And although ideally I would like to think that in an ideal situation, a scientist would justify his findings using the scientific method, and that would end his responsibility. However, that is not the case, and especially in what you have been saying, where public health is concerned. So my question is, what can we do to bridge that gap?
That's a great question, and this is very complicated. So for just real quick, I also want to say, as the multidisciplinary person in me, there's a big difference between scientists and engineers, and they can overlap. So we have, I'm a scientist and an engineer, but science takes a perspective from a very limited angle. And yes, we can reproduce this, and we apply the scientific method to verify our findings and draw conclusions. But as engineers, there's a wide variety of problems that we have to solve and design around. And so scientists aren't necessarily concerned with implementation or making the solution for the problem as much as they are describing, defining, and outlining that problem and maybe where it comes from and why. As engineers, we want to know what to do about it, right? And so that's sort of where regulation overlaps with science. Is science says, hey, this is bad, take it out. We've got PFAS in baby's blood, right? We know it's bad, it causes cancer. And then as engineers, we go, how can we take it out? And as public health engineers, we have to say, well, who wants that? Where's the driver for that? Is there regulation around it? I mean, there's probably a lot of things like that we shouldn't do, from eating sugar and drinking sodas that are bad for our health, but we make those decisions as individuals in our free society. So like basically engineers go, how can I make a utility like implement this change? So by and large, the modern challenges around public health and engineering are around that communication and that regulation and that public advocacy. And to your point, there is a giant disconnect between what the public thinks is important and what science says is important. So we've actually run a survey before on the public perceptions of like, what's the most dangerous aspect that's scaring you from drinking tap water, or what are you afraid of? And a lot of the public is afraid of fluoride, or they're afraid of different types of things that are good for them, because they're not educated. So what we can do as engineers is bring again best practices. Hey, this has been done for 30 years and it works and nobody died from it. Best practices, and then communicate those best practices. But you're absolutely correct in identifying this gap between science and engineered solutions and implementing those engineered solutions, because we can't just like tell people what to do. Where's the money going to come from to fix the problem, and how will people even want to support that? So it's kind of difficult, and that's a very good question, because it brings back to the point that this is just more complicated than, say, just solving the problem or proving the problem exists. You have to get the public on board, and then if there is no regulation, no one's going to make them do it. It's just going to bring the cost back up, where people are already complaining about the cost of water. So it's a really weird, it's a great question, and it's something that we all should think about, because I think as engineers, it's easy to kind of think, well, we'll just go solve the problem. We'll just do, an equation, and we'll write the math out, and we'll do a design. Well, number one, these are different everywhere. And two, not all the regulations are implemented in different states. California has different regulations than Texas. And so the willpower and convincing the whole public, especially from a national level, it gets kind of hard. And all of these decisions are always made around money. Always made around, right, what we can spend. But that's I don't know if I answered the question. I was kind of convoluted there, but that's a great point. There's a gap, and communication's the only thing that's going to really fill it.
Thank you.
Thank you for your question.
So Dr. Himali, before you close, I just want to request Dr. Shin, if he is available. Do you want to announce the next webinar, which we are going to host on 20th of Feb? Dr. Shin, are you here? I think he's not here. So let me just announce, we are going to have another webinar on 20th of February. Soon we are going to share the detail of the speaker, bio, and similar registration process. And I invite you all to please attend that webinar and have a similar kind of experience which we had today from Dr. Deema. She really explained really nicely from I would say from zero to infinity, like how to touch everything. So really nice presentation, Dr. Deema. And over to you, Dr. Himali.
Yeah, again, thank you, Dr. Deema, and I really appreciate you dedicating your valuable time to enlighten all of us. And I'm really sure that all of our budding engineers learn so much from you. And I'm really thankful. So everyone, please join me to give Dr. Deema a virtual applause for her excellent presentation and sharing her wisdom with us. And thank you so much.
Thank
Bye.
you. Thank you again, Dr. Nitan and Dr. Himali. Thank you so much for having me. And again, I dropped my email in the chat. If anybody wants to ask me any further questions, feel free to reach out. And thank you so much for extending your audience and your attention.
Thank you.
Thank you, everyone.
Have a great week, everyone.
You too. Bye.